where this stuff shows up and what uses it has in real life. And then we come at it with the math. Oh, and I want to show you why this thing is called conic sections. Why do you think, what would that phrase mean to you? Some of you guys might have read ahead, which would be kick-ass. But what would conic sections, what the hell, conic relates to what? Cone. A cone. And then sections would be if I take that cone and I start cutting the hell out of it, right? Section it. Right? A cross-section of something would be if I cut it and I looked at it, cross-section. So conic sections must be some kind of cuts that I make into a cone. So a really good question would be, how the hell does that relate to anything mathematical? Because math loves to analyze graphs. Okay, yeah, that's perfect. Oh, sure. Let's see. Wow. That's large. So if you take a cone and you cut it straight through, anywhere along the cone's axis, if you cut it straight through, you're going to make a circle. It's going to be perfectly symmetric, a beautiful little circle, because it's circular at the bottom. That's the whole definition of a cone. Right? Circular at the bottom, comes together at the top. Wigwam, kind of teepee kind of thing. If you come at it not straight through, but come at it at a diagonal, you end up with an ellipse. It's longer in one dimension than it is the other one. So that's a squished circle. If you come at it so that it doesn't go all the way to the other side, so it doesn't come back together, you get either a parabola or a hyperbola. And to really get the full idea of hyperbola, you need the other side. Let me see here. Stop. It's really going to mess with the resolution screen. Here. There you go. So if I have two cones on top of each other like that, I don't know if any of you have ever heard of the time cone. It sounds like a really bad sci-fi series that you're going to try to put on the sci-fi channel, but it's not. All it doesn't matter. If I put two cones like this, and I cut straight down, you see how that hyperbola is going to have two parts to it. It's going to have one part facing that way, and one part facing the other way. Of course, a parabola does not have that other part because it's going to miss the lower ellipse, the lower cone. You guys see that? That's why it's called conic sections. Beautiful. So let's really get into the math of it. And of course, you guys are going to be graphing these things based on the equations you get. So you have to know how to interpret the equations you get. So first of all, we already know a parabola, but to tell you honestly, you don't know it as well as you think. So somebody tell me the equation for a parabola. I love it. Right? So the most basic parabola I know is y equals x squared. Now, that's not nearly good enough. I need to, and let me start off, let me say, okay, that's what we know about parabola so far. We need to fill in our knowledge a little bit to help motivate us as to how to do that. Does anybody know an equation of a circle?
Something like y equals ax, no.
Y squared equals x squared.
Not quite.
Y squared equals x squared equals something.
And in fact, let's figure it out. I love it. This is one of two things that could have happened. Either we knew or we didn't. And if we don't know, it's almost better. Let's say I have a circle with the origin as the center. So how would you describe a circle to somebody who has no idea what a circle is and can't see it? So you can't just draw it. Here's a circle. How would you sort of mathematically describe what a circle really is?
Same length radius all the way around.
Every single point on it is the same distance from the center. Good. So every single point on this, any point on this has to be the same distance from the center. I love it. So what is the distance between that point and that point? And so this point, does it have to be where I put it? That point x, y, does it have to be right there? It could be anywhere. It could be that point, it could be that point, it could be that point. It doesn't matter. So x, y is the most general point possible. Right? So what is the distance between these 2 points? How do you find the distance between 2 points? What formula do you use? You probably use the distance formula. That's crazy. Right? That's just silly. And the distance formula is really based on the Pythagorean theorem. So I don't know if you guys remember the distance formula. I mean, to find the distance between 1, 1, let's make it 1, 2, and 3, 5. Maybe this will jog some memories. Yeah, it would be 3 minus 1 squared plus 5 minus 2 squared. Because, of course, if I want to know this between 1, 2 and 3, 5, it's just the hypotenuse of this triangle. So if I know y2 minus y1 and I know x2 minus x1, how do I get this? That squared plus that squared equals that squared. Right? Pythagorean theorem. The square root comes because I don't want d squared. I want d. I want the distance. Don't tell me I live 400 square miles away from here. That doesn't make any sense. So how do I do the distance between this and this? So, careful. Do it again. The difference in the x's. X minus 0 is x squared plus the difference in the y's squared. And do we normally call it d? What do we normally call that distance? R. And of course, what do I do to both sides to kind of get rid of that square root? Squared. So I end up with x squared plus y squared equals r squared. That's the equation of a circle that's centered at the origin. Could anybody tell me? First off, what can you tell me more specifically about that circle? No, you can't say that. You can't take the square root of each piece. Square roots don't distribute. The only thing you really tell me is radius is 4. And it's a lot like y equals mx plus b. If I put it in the right format, I can see things about it. If I put a line into y equals mx plus b, I can see the y-intercept, I can see the slope. If I put a circle into this form, I can see the center is 0, 0, because the x and y haven't moved at all. Some of you guys might be like, what the hell do you mean by that? And the radius has got to be the square root of 16, 4. So how would I write this if I wanted a radius 4, so I'll do that part for you. But I want the center to be at 1, negative 3. How would I do that? How far do I have to move left or right? To get, what is the center here? What's the center for this one? 0, 0. So now I'm talking about transformations, right? I'm talking about translations. How do I make this sucker move over 1? How do I make anything move over 1? Remember that? If it's in with the variable, it's the opposite. So that would move over 1. Here's something a little different. I got to put this one in with the y, so what would it look like inside here? Plus 3. So that would be a circle of radius 4 and center 1, negative 3. Is that cool? Okay. So coming back to a parabola, I need a more formal definition telling me what the points on a parabola are. Here I know the points in a circle are all the same distance away from the center. And the center doesn't have to be 0, 0. Be somewhere else. But for a parabola, what the hell are the parameters? So a parabola, believe it or not, I got to bring in this idea of directrix. And actually, let me go ahead and give you the handout so you can kind of follow along as we do this. Then you'll know all the answers ahead. So there's two sides to this. There's the purely technical side, and then there's the how do I actually do this? What's the practical? How do I get this on my graph paper side? So I have a little bit of both on this handout, and it's basically the same thing the book has. I just wanted to try to collect it all into one place. So you can see that the definition, if I take any arbitrary point x, y, a parabola is going to be the set of all points that are equidistant from the focus and the directrix. So my example, it looks kind of gross, but oh, give me some board license. So, let me see, how much do I want to do with this? I can do a little bit. So the definition of a parabola, then, let me make this a little bit more general. There we go. It's not straight across. Is that these two distances have to be the same, right? And they tell you that the focus, if you look on page, where am I at? Page 726? No. 725. Let's start with these. This one is negative p. This one's down p. The focus will be up p, basically. Right? And then we'll also talk about parabolas that open left or right next. And all I have to do for those is just switch the x and y. What's the distance between this point here and this point? What's that distance first? We'll call this d1 and we'll call this d2. So what's d1? What's that distance between these 2 points?
D2. Doesn't it have to be the same?
Yes. So in order to get the equation, what I'm going to do is I'm going to get an expression for d1, an expression for d2, and then set them equal to each other. So I don't want to use the fact that they're equal too early, or else I don't get anywhere. So by itself, what's d1? What's that distance there? Going to be going to start off square root of x squared.
What is that? I can't read that.
Yeah, so p.
Oh, yeah.
So y minus p squared. So that's the distance for those two. That's d1. What's d2? d2 is a lot easier than you might think, possibly.
0. Square root of 0 squared. Right?
Yeah, well, so this point, what would this point here be?
X something else. Next.
Yeah, it'll be whatever x is, and then negative p. I like it.
Exactly negative p?
Exactly negative p. Because the directrix is y equals negative p. It's always down p. Right, so this line here is y equals negative p. So every single y point on that line has to be negative p. That's the definition of the line. So how far apart are those 2 points? Like you said, it would be 0 squared. And then, what's this here?
Y plus p.
Y plus p squared. And of course, what's that? You got to be a little careful. What's the square root of y plus p squared?
Y plus p.
Sort of, almost. It's the absolute value of y plus p. But the nice thing is, I know that in this case, y is positive and p is positive. So the whole thing comes out positive. You guys semi with me here? A little tiny bit? So, I mean, this is how we construct formulas from things. We can actually construct what the formula for a certain shape is supposed to be. So if I want a shape that does something, I set down all the things I want it to do, then I translate all those things into math, and then I see what that leads me to. It gives me an equation that does all those things. This is kind of like your first little baby step into constructing a graph that does what you want it to do. So what are these two supposed to be? Equal to each other. So I have the square root of x squared plus y minus p squared has to equal y plus p. And the first thing I can do is take a square of both sides to kill that square root. You guys kind of with it? So if I square both sides, I get x squared plus y minus p squared equals y plus p squared. I don't need the absolute value anymore because that's definitely going to be positive. And now I just kind of work with this until I get somewhere. So if I FOIL this bad boy out, FOIL that bad boy out, you see a lot of stuff that cancels, which is really kick-ass. All right, so the y squares and the p squares all cancel. If I add this over, I end up with x squared equals 4py. That is the official formula, the official standard form for a parabola. Because it came from the definition of what we want this to mean. We want it to be the collection of all points that are the same distance away from that line and that point. So a concrete example, please dear God. Concrete example, and I gave you one on the handout actually. If I have this equation, 3x squared equals 36y, I know that I don't want that 3 there, so I divide that 3 out of the way. And then this tells me what form to try to force that to be in. So of course to match this form, I just want to factor the 4 out of this. So I'm going to x squared equals 4 times 3y.
So p is 3.
So p is 3. Which means what? If you guys see that, so p must be 3 because I put it in the right form, therefore that part jumps out. Now we'll say this. I don't, even though we kind of went through this a little bit technically, this form for parabola is not used very often, but it's kind of good to see it being created. The form for the ellipses and the hyperbolas, now that we've gone through this once, when I go through those, it'll make a little more sense, hopefully. So we'll see what those definitions are, what mathematical equations they lead to. So for right now, if p is 3, the focus must be at 0, 3. And the direct roots must be where?
-3.
Y equals -3. Cool. And if any of you guys are at all interested in, astronomy or anything, you have, or even how they make spotlights, for example. When you're driving downtown, they have those spotlights going off. You have these parabolic mirrors, and they have a focal point. So if anybody's at all interested in even, this is roughly related to lenses and their focal point. So if anybody's into photography, the same kind of thing. If that is the focal point where if light rays come in, they would all gather at that point. If light rays came in from infinity, they would all gather at that point. Or if I have a light source here, the light rays would all bounce straight out. That's why you have such a focused beam. They have a parabolic mirror. They put a little light bulb here, or a big ass light bulb there. When all the light bounces off, they all come out the same way, the same direction. So it's very focused. You kind of with me? A little bit, okay? So again, it's a really neat application, and the math helps you if you want very specific parameters. It's got to fit somewhere, or you want it to have some area of light coming out. You got to set up your equations and see what would make that work. Okay, maybe. Yeah.
How did you get p equals 3 again? Sorry.
Oh, you're cool up to here?
Yeah.
So then, to make it look like this, I have to have 4 times something times y. So right now I have 12 times y. So just take a 4 out.
Oh, okay.
So 4 times 3 times y. So p must be 3 because that's what's in that place. And we're used to that kind of thing. You solve and you get y equals 2x minus 7. You know what the slope is. You know what the y-intercept is. Just because they're in the right place. Same thing here. Just because it's in the right place, it's that. I like it.
Wait, where'd you get x squared equals 12y?
Oh, just divide. So I was given this. Given that equation. Then I divided by 3.
So is that where we started that from?
No, so this is all, I started with, you guys know what parabola is. We went into the definition of what a parabola should be. We did the math to see what form that would lead us to. And then here's a specific example. If you're given this equation, the first thing you want to do is kill the 3 because you don't want a 3 there. And the next thing you want to do is take a 4 out because you want a 4 times something.
Okay, I just looked up and you wrote that and I was like, okay. I didn't know where that came from.
So that's a specific example there. So moving on to ellipses, and the really cool thing about ellipses is they're very similar to, very similar to circles. So it's really nice to see the equation come out the way it does for ellipses. And the definition of an ellipse. The difference between a circle and an ellipse is that a circle really has one, what we might call a focus. We don't really call it focus, it's the center. Whereas an ellipse tears that apart into 2. And the further those 2 get apart, so these are the foci, right? Just fun to say. The further I pull those apart, the more squashed my ellipse becomes. Because, of course, the more I push them back together, if I push them back together, they're getting closer and closer to a circle. So the more I pull them apart, the more flattened it becomes. Whereas if I start with a circle and pull them this way, I get this kind of ellipse. Right? Or UFO. So, what is the definition of an ellipse? The points on an ellipse. And of course, you guys all have it there. It's the set of all points where this distance plus this distance is a constant. And you can kind of see ahead, a hyperbola is the one where the difference of those distances is a constant. So this one is, since these 2 have to add to be a constant, let me give you an idea of why this is closed, and why hyperbola is open. Right? You can kind of see ahead on the picture, hyperbola is going to be open, out, and that ellipse is like pulling those together and making a loop. It's closed. Give me 2 numbers that add to be 7.
3 and 4.
I love 3 and 4.
2 and 5.
4 and 3, 2 and 5. So when one goes up, the other one has to go down. They kind of keep each other in check. So if I say the maximum number either of these could be is 8, then it would be up to, let's say 7, and the lowest it could be is 0. It would of course go from 7 plus 0 to 0 plus 7. So it's kind of contained. Whereas if I say, what 2 numbers subtract to be 7? 10 minus 3, right? 12 minus 5.
1 million.
1 million minus whatever. Right? So it's a little more open. So when I say 2 things there has to be a total, that kind of is a constraint on me. I have to stay in. If I say 2 things, difference is a constant that allows me to go to infinity in some direction. So let's look at the implications of this. So this is where things get a little bit more freaky. So if I have some point x, y, and they have to give me something to start with. Let's say this is at the origin, thank God. The center is not off somewhere else. In fact, they don't use the letter C for these. So this one would be C and negative C. So for ellipses and hyperbolas, they use the letter C for the focus, for the foci. And you'll see why. There will be a formula that looks very familiar coming out of all this in a minute. So what's this D1 distance? Yeah, good. So x minus negative c is x plus c. Let's go see how long it's going to stand there. So x minus negative c is x plus c. Y minus 0 is y. And what's d2? Yeah, square root of x minus c squared, and again, plus y squared. Cool? Now the really nice thing, and I don't remember if they do this in the book or not. Hopefully they do. Makes it all very simple. Oh yeah, page 733. Well, alright, they do it the really disgusting way. Okay. So we'll do it the same way. And actually, let's see how far we can go through this. So I want this distance plus that distance to be a constant. And if I want it to be a constant, I can call it A, B, C. I can call it whatever I want it to be. I can call it R. Not really going to have a radius here, but I could. So we're going to call it 2A. Just because we kind of know ahead of time something weird is going to happen. So if you called it A, at some point in this whole process, you'll be like, man, I wish I would have called that 2A. That would have made this a lot easier. So here's where you guys really love doing these kind of problems. What must I do to start trying to solve this thing for X or Y, trying to get this thing simplified a little bit? What do I have to do? What really, really sucks about that equation? I mean, what do I have in there that I have to take care of? Square roots, and the fact that there's two of them sucks. Right? If you don't realize that, it just does. And because I have to square twice, I can't just square each piece. Please, dear God, you are not allowed to do that. Ain't no way. If you square one side, you got to square the other side. If I square the side, I have to FOIL. So I'd really rather not FOIL two roots together. I could move one of them over to the other side. So if we rewrite this as and then square both sides. I'll do this side. Did by half. You guys do that side. So write the thing twice, FOIL it out. Don't worry, we're not going to do this for hyperbola also. We'll just say it's very similar for hyperbola. And they've got the proof there in the book. But I do want to do this at least once. So if you write this thing twice. What do you get when you FOIL this out? We get 4a squared. Minus 2a of these, minus 2a of these, so minus 4a of these. Cool? Because the middle stuff's going to be the same. They'll be like terms. You can put those together. And what do you get at the end? What is this thing times itself? Yeah, the inside. 11.
C squared.
Square root of 11 times square root of 11 is 11. Right? For two reasons. Square root of 11 squared, the square root and the square cancel. But a better way is half of 11 times half of 11 is a whole 11. That's a nice way. So this half and that half makes a whole this thing. Alright. Hoping that I lost everybody. What's really horrible that we knew was going to happen, because there were two roots to begin with, I knew eventually I'd have to square twice. But let's try to clean this up a little bit if we can. Got a really old marker. If I FOIL this thing out, And then if I foil this thing out, you'll see a lot of stuff cancel again. Sort of like we did with a parabola, except here it's just worse. There were more roots thrown around, so it's going to be a little bit worse. But I see a lot of stuff cancel. Right? See like the x squares, c squares, y squares. That's cool. I don't want to keep writing that stuff down. How we doing? And if I add this part over, I'm going to try to minimize the amount of writing I'm doing here. Just because it's negative over there. Now, if I subtract that part over there, I'll get 4a squared. I move that over. Subtract 2xe. I'll get there. Is that cool? So subtract that part over. That's where that came from. Move that there. And there's the 4a squared. Everything else canceled. That's nice. It looks a lot better. And then I could, of course, kill the what dies really nicely here. The 4s can't die, right? So I can just kill the 4s. And then I could divide by a, but I don't want to. So what do I get if I square both sides now? This side I'll get a squared times this mess here. Is that cool? The square root just goes away, the a outside gets squared. And this side, if I just FOIL it out, I get a to the 4th minus, let's see, 2a squared xc plus xc squared. Nice and gruesome. But now at least I don't have any square roots left, right? The very first thing I could do, we might as well go ahead and kill the a squared. So let's see what we get. We get x minus c squared plus y squared equals a squared minus 2xc plus... Just dividing everything by a squared. Now if I FOIL that bad boy out, does anybody see something nice happen from that? And I know that a lot of you guys, and if you don't want to write, I know that a lot of you guys are writing this stuff down. It's all on page 733. And much better for it. But so often we give up on a problem way too early. Just one more step, a bunch of crap would cancel, like right here. A bunch of stuff cancel. But a lot of people right here say, oh, there's too much shit going on there. I do not want to do that. Even here, oh, there's too much shit going on there. But if you FOIL this thing out, what happens? What do I get in the middle here? Cx, so I get minus 2cx. So of course those go in. Right? And so finally, let's see, let me gather what I've got here. Get in there. Gruesome. Oh, there it is. Okay. Cool. So the form I'm trying to get to, the part that I don't remember. Oh, that's right. Yeah, we can do that. Okay. So if I do something not the most obvious thing in the world, but if I divide through by c squared, I'll get x squared plus y squared over c squared plus 1 equals a squared over c squared plus x squared over a squared. Yeah, it's kind of freaky. So if I subtract this over, I'll get x squared plus y squared over c squared minus x squared over a squared. let me see, was it the other way I'm supposed to go? Let's see. Equals a squared over c squared minus 1.
Can you do that again?
Oh yeah, so all I did was subtracted 1 that way, and subtracted that this way.
No, from the beginning. I'm not following that.
Which part? Sorry.
When you divided by c squared?
Oh, so if I divide by c squared, I divided both of these by c squared.
Okay, I get that.
C squared divided by c squared is 1.
Okay.
A squared divided by c squared.
Okay.
And here the c squared just cancels.
Okay. Got it.
So if I get my c squared stuff together, let's see which way I want to go. Yeah, that's right. So I've got everything kind of backwards, but that's all right. So, see these two have the same denominator? That might be useful. And then that guy's off by itself. Let me see. Which way do I want to go here? Okay. Oh, okay. So if I've got, go one step back here. If I multiply all this by a squared c squared, I'll get a squared times this minus a to the 4th minus x squared c squared equals negative a squared c squared. And then if I pull this through, I'll get x squared a squared plus y squared a squared So now look at the x squares. I have x squared times a squared minus c squared plus y squared times a squared. And when we push this over this side equals a to the 4th minus a squared c squared. Okay, so of course, I kind of know where I want this to go. Remember what, from the very beginning, we knew that ellipses were very much related to circles. So I should expect to have a formula that comes out sort of like x squared plus y squared equals r squared, but not that, because that would be a circle. But it should be close to that. So you see where we're getting, we got the x squared and the y squared, you see that? And why does it make sense that they don't have the same coefficients? Because for an ellipse, is it symmetric in all directions, like a circle is? No, it's not symmetric. One dimension is longer than the other one. So that they should have different coefficients. That should not bother us, that that's true. So if I divide everything through by each of those, I get to almost where I want to be. I get to exactly where I want to be. That's cool. So if I divide through by this and that, on this side I'll get 1. On this side I'll get x squared over a squared plus y squared, and we call this part b squared. So c squared equals a squared minus b squared. That's definitely different than the Pythagorean theorem. That's not the Pythagorean theorem. But the way I remember this is an ellipse has a plus in the equation, so in its focus equation it has a minus. Hyperbola is going to have a minus in its equation, so in its focus equation it's going to have a plus. It's always, if it's minus in one, it's plus in the other one. So it's the kind of way I remember this. So this is the form of an ellipse. That looks a lot better than what it seemed like it was going towards, right? That looks really nice. This was insane. But a lot of stuff canceled out on the way, thank God. Alright, so that's the theory, which is always rough to go through. I totally understand that. Let's look at the concrete reality. Let's get a real problem and try it out. I'll do a different one than the one I've got on the handout. At the bottom, or in the middle there, I've got a problem worked out. Let's try a different one. So basically, a circle would be like x squared plus y squared equals 16. Whereas an ellipse would be x squared over 4 plus y squared over 1 equals 16. You do this even better. I know where I want to go. Let's just start this way. There, that's better. So different coefficients, like I said earlier, right? The coefficients aren't both 1. For a circle, they're both 1. For an ellipse, they could be 4 and 1. Now, from the form, what's kind of off here? What's not supposed to be there that's there?
You need to divide.
Yeah, I need to divide by
4.
even better. By 16.
Oh.
Right? So if I divide by 16, because I know I want a 1 here. If I get a 1 there, everything else falls into place. So if I divide by 16, I'll get x squared over 4 plus y squared over 16 equals 1. So here's how all these numbers kind of play in. Can anybody tell me, what would x have to be when y is 0? So that shouldn't be that tremendous of a problem. If y is 0, what's x?
4 or 2, since it's squared.
Yeah, it's got to be 2, right? You with me? If y is 0, this has to be 1 by itself, so x would be 2. Could x be bigger than 2? Or, in fact, negative 2, right? That could be the other option. Could x be bigger than 2 or less than negative 2? If x were 3, think about it. This number would be bigger than 1. This is always positive, so there's no way to get it back to 1. You guys with me? That's the whole reason why it keeps itself closed. It doesn't let it go off to infinity. There's constraints on it. Hyperbola actually is more like a restraining order. It says you can only get this close. Whereas ellipse is, stay close to me. Here's the breakdown. Now, on the handout, you have all the technical, you have the semi-major axis and semi-minor axis, all these, the names of what's going on. Here's the beauty of it. We've already established that on the x-axis, it can go down to negative 2 and up to 2. So we say a squared is 4. See the 4? A squared is 4, so then a is 2. And we don't really put plus or minus there. It's a distance. It can go 2 away from the center, left and right. Cool? And of course for the y, b would be 4. So it can go up to 4, down to negative 4. How we do? So ellipse is really stupid easy to draw. You can really just look at, you know it's going to be longer in the y direction. Since I'm dividing by a bigger number, y can be a little bigger. So it's going to go longer in the y direction than it is in the x. It's going to go up to 4 and down to negative 4. Over to 2, down to negative 2. So you just draw in those intercepts and then fill in the ellipse as best you can. Personally, I draw with much left to be desired. So that's not bad for me. It's like Stewie napping. So that's the beauty of it. It was ugly to get to the equation, but every equation that we use and interpret, you've got to realize there's a lot of math that went into creating it. Started with a definition, ugly math, a lot of stuff canceled. We end up with this beautiful little expression. And then the math is, please let that math be easy. There's not much to it. The one thing I haven't done yet that we used a lot in the problem is what's the focus? What's the foci? So c squared equals
4.
good. And I'll tell you this right now. I'll tell you this. I was taught a different way than the books have it nowadays. And they make the A and the B switch based on which one's bigger. I just always said to myself, A is X and B is Y. And then when I go to do this, I just subtract the bigger one minus the smaller one. So the book tries to change the A and the B so that it's always the same formula, but who cares? You know you're going to take the bigger minus the smaller. You can't have an imaginary focus for this. So I'm going to do c squared equals a squared minus b squared. Do these really matter? No. Bigger minus smaller. So c squared equals 12. So c equals square root of 12, which is simplified to
2 root 3.
I like it, right? It's 4 times 3, so it'll be 2 rad 3. I like it. So, hello. So my foci will be at, and of course 2 rad 3 is roughly 3.4 or something. Somebody did that, I think. So one focus would be here, and another focus would be there. 3.4, negative 3.4. And would you say that this is close to being a circle? I mean, it's 4 big and 1 wide, so that's pretty far away from being a circle. You with me? So it makes sense that the foci are so pulled away from the center. If I push it to the center, this becomes more circular. The more I pull it out, the less circular it becomes. And they're way at the edges. Assuming that I did my multiplying right in my head. Cool. All right. So that's cool. So that was a lot to go through for the derivation. It always is. But then the actual use of where we end up, let that part be easy. That part is nothing special. So I'm going to let you guys do a real quick ellipse problem on your own. First, very quickly, rederive the depth. No, I'm joking. Yeah.
How do you know where to place the foci?
Oh, they always go on the longer axis.
Okay.
Good question. If they went on the shorter axis, they'd be outside the picture.
Yeah, that's just what I was thinking.
Yeah.
On the A, B, isn't A2 and B?
So again,
Did I miss something?
there's whenever. So let me see if I can explain this. Whenever you try to generalize something, and like the book attempts to, and it changes the A and the B, I always hated that, and I wasn't taught that way actually. I was just taught that whichever one's bigger is going to be the longer axis, which makes sense. And when you want to get the focus, it's the bigger one minus the smaller one. So then you don't have to have a definition where A and B move around. So you have to realize that, and I either have to be careful or just do it the way that makes sense. And I'm going to do it the way that makes sense. So I could always try to force it to be the B and the A switch, if whatever. I don't like that stuff. I always say to myself, A is there, B is there. You can do it the book way, or you can do it just the way that makes sense. So if I want to get a focus, it's got to be a real focus. So I have to do the big U minus the small u. A and B are completely arbitrary variables. You with me? You could force them to be this one be B and this one be A, make A always the bigger one, so that your formula would always make sense by itself. Yeah.
So if we got a negative one, we just should know to switch it?
Exactly. You shouldn't do that in the first place. It should always be bigger number minus smaller number. Cool. And that's really the only reason that the book defines A and B the way it does, is to always make this come out positive. Well, instead of going crazy remembering what A and B is, just make this come out positive, right? So here, you guys try this one. What you got? It's not too bad.
got a quick question. What do the foci actually do? Like,
So they're the ones that, if it was a circle, they would actually both be one thing in the middle. So the minute I rip those apart into two and start moving them away from each other, then the ellipse starts to form. That's what squishes it up. So if I pull it up and down, then it would become like that shape, like the one we just got. And then of course you realize you could do diagonally, but then the math gets really gross. Rotating something makes the math
terrible.
Yeah.
For sure.
So we're only going to focus with along one axis or along the other axis. Yeah. So what's the first step on this problem?
Divide by 36.
Yeah, divide by 36. So you get x squared over 4 plus y squared over 9 equals 1. Now, of course, I mean, you could make problems where it's over 7, so then it's radical 7. There's really no big reason for that. Yeah.
So right away you know this is a vertical since the y is larger.
I like y's larger here, so it's going to be another one like that. It's going to be longer along the y-axis. The foci are both going to be on the y-axis. Yeah.
Are you going to give us problems where it's not going to go and eat like that?
I'm going to show you one after this. That is the kind of problem that you'll see. I'm not really going to make the numbers, come out disgusting. There's no real reason for that. But I could do one other thing. You could then define A as 2, B as 3. C squared would be
Root 5.
9 minus 4, C squared is 5, so C is root 5. Can't really simplify that, so you just leave that alone. The A and B definition don't really matter. So I'm always torn between, and I just wanted to do it the way the book did it, but then I wanted to talk to you in class about, what really makes sense. What's the practical use of this stuff? So when you're trying to generalize something, it's always going to be worse than if you do a specific problem. So I know I always want to make them come out positive, so I don't have to remember all the A minus B, which way is it? So here, how far do I go on the y-axis? 3. So I'm going to go 1, 2, 3 up, 1, 2, 3 down. And of course, on the x-axis, 2. So then I put in my points, and then I do the best I can on the. Oh yeah, it's awesome. As long as it depends on the way you make your scale, but just be careful not to throw your scale off too much because then it can be circular. If you graph things on your TI, if you graph a circle on your TI, it's going to look like an ellipse because your window is not square. You see what I'm saying? So it's always kind of like smushing things, which never really made sense to me. I'm like, why don't they just make a damn square freaking window? Yeah.
You said for like the foci on ellipses, it's always going to be a squared minus b squared, then on parabolas, it's going to be a squared plus b squared.
For parabolas, hyperbolas, exactly. So I always remember an ellipse has a plus in the equation. If I were to make this a hyperbola, I'd just put a minus there. So an ellipse has the plus here, so it has the minus in the C equation. A hyperbola has a minus here, so it has a plus in its focus equation. Does that kind of makes sense? That's how I remember which way it goes. Okay, cool. So we keep talking about hyperbolas. Let's look at hyperbola. And we're going to do the associated hyperbola. That's what I'm going to call it. So if I had, all a hyperbola is it's going to look basically something like that, or like that. So one really good question would be, well, when the hell is it sitting on the x-axis, right? This first one would be what I call sit on the x-axis, because it actually touches the x-axis. Or when is it going to be sitting on the y-axis? Oh, and before I go there, I did promise you I was going to show you one last thing on ellipse. One last ellipse. If I have this, actually, I gave something away there. Too bad. It's already 1 here, right? So there's nothing to divide. But A is not 4. A squared is supposed to be the thing on the bottom. There's supposed to be a 1 here, right? The form of it is x squared over x squared, y squared over b squared equals 1. So there's supposed to be a 1 here. There's supposed to be stuff on the bottom. So of course I gave it away a second ago. How do I make that 4 go on the bottom? It multiplied by 1/4. I can just take it down as a 1/4. So what's A? 1/2. Right, that's A squared. So A is the square root of that. And what's B? 1. And then you would just make your scale so that you fit 1/2 in nicely. You guys kind of with me? Cool. So if there's a number out front, you just do the reciprocal of it down below. And that would be your A squared or your B squared, however you want to look at it. That's the only other freaky thing that I would kind of do to you. In the homework, there might be a few where you get like radical 7. But you just approximate that, not a big deal. On a test, I normally make the numbers come out nice enough. At worst, I give you like 9/4, so then the square root would be 3/2. But it's still nothing like a radical or something, you would be. Because I'm more curious about, do you know where things come from? Do you know how to use them? Not, do you know approximately where square root of 7 is? You should. Okay, so one big question would be, when does it look like which one of these? So if I take that same formula, and the only thing I do instead is put a minus in the middle. So over here, the smallest either one of these can really be is 0. Because if I make x negative, it's still going to be positive when I square it. You with me? So the plus, in that case, is just like I was saying earlier. It kind of keeps it closed. If one goes down to 0, the other one can only go up so much, so forth. This minus has the opposite effect, right? I can actually, in this case, I can let x get stupid big as long as y also gets really big, and it's going to still bring it back down to 1. So that's why this goes to infinity in some direction, right? So can anybody figure out, is it going to be this A or this B? Which picture would this relate to? And one way to think about it is, where are the intercepts that exist? One variable has imaginary intercepts, and the other one has real intercepts. And the ones that are real are the ones we'd see. We're not graphing imaginary stuff in this class. So which variable has real intercepts?
A dot x. The x variable?
Yeah, the x variable has real intercepts. So it's got to be A. The x variable has real intercepts. Can you solve that for a real number? Right? Once you get y squared equals -9, we're screwed there. Right? So there's no real y-intercept. So it must be this picture. So the shortcut there is whatever variable is positive is the axis it's going to sit on. Right? If that was y squared, it would have sat on the y-axis.
So one of them is going to be associated with the 4, and one's going to be a different. It's not going to be like some.
No, it actually will still be associated with a 9. And I'll show you how. And it's kind of cool. And really, well, one way I teach this is to go back to something that we would have done in trig. But not everybody in here has had trig. So that's too bad for me. Because it's kind of a cool thing if anybody's ever had trig. How many of you guys have done trig? Remember how cosine and secant, the graphs are related? Cosine's kind of closed and secant is sitting on top of it. So, and the rest of you guys are like, can you talk to me too, Jeff? Ellipses are closed. Hyperbolas are open, either that way or that way. So a hyperbola should somehow be directly related to its ellipse. There's a plus, there's a minus. So sort of like, instead of coming together like this, it's just going to open the other way apart because of that minus. So the shortcut to kind of get there, there's a lot of stuff that goes into this. And this is the x direction, this is the y direction. So again, I can say A is 2, B is 3. Up on the board, I'm just going to do it the way that makes sense. The book has very specific times when one is B and one is A, and that to me is just not useful. Why waste my time on it? Let me just do what makes sense. So I know somehow I'm going to go in the x direction 2, and in the y direction 3, sort of like I did for the ellipse. So those are going to have some kind of importance. Which one of those is going to be your real point? We said this earlier. Yeah, that's going to, the 2 is going to be the x-intercepts, right? 2 and -2. So here I'm just going to put a little circle. This is not really a real point. You guys with me? That's an imaginary something or other. That's no good. All right. Maybe. So I know the shape of it. I know here would be the ellipse. That ellipse there. Hyperbola is going to somehow be this shape. To get the guiding, to get what guides me as to how to shape this thing, I could do one of two things. I could do as the book instructs and make a little equation of an asymptote, which is fine. There's nothing wrong with that. And let's actually do that once. Slope would be whatever what in general? What's slope? In general, slope? Rise over run. Rise is the y's, run is the x's. You with me? So it would be 3 over 2. So that's how you get that asymptote very quickly. Now, of course, the book has got b over a or a over b. I desperately want you to be with me here, because if you look at the book, it's got a very specific thing it does with the a and the b just to make everything consistent. But do I really need to do that? No. I know what slope is. It's the y piece, bam, over the x piece, bam. I don't need to know when to switch a and b. I know what it is already. So I could draw those in. This is actually going to be plus or minus those. Because again, in reality, a and b are plus and minus, right? Because they're squares. You with me? And I could draw those in. But a much quicker way to get those same lines drawn without even getting the equation is to do what's called the box method. You draw a box in on top of your points you've already drawn in, just like that. You with me? And then through the corners, you draw your asymptotes. Now what's the slope of this line? Of 3? Over 2. Bam. It's 3x x, right? I didn't need to get the equation. It's a really cool way to get the box. I already have the x and y points. That's what would go together to make the equation. But why make an equation and then graph if I can just graph based off of what I already know is here? I don't need to have that middle step to make the equation, really. And then back through the other corners. And that's my asymptotes. They work just like any other asymptote would. My function has to go out and get close to those. So they're my guides as to how fat my hyperbola is and how skinny my hyperbola is. So you can see if I had a box like this, it would be really skinny hyperbola, right? My asymptote would come out and it would be really skinny in there. This one's a little bit longer this way, so I got a nice fat hyperbola. So what would it look like if it was... Oops. Everything I've done would be fine, except what's the only difference if it would have been that? It would be sitting on the y. So that would be the real point. These would be the fake points. And I would just draw it up here. That kicks so much ass. And notice, where's my hyperbola, my ellipse? My ellipses would be, my associated ellipses in there. That's really good, Jeff. Wow. Well, that's about as bad. Oh, sorry. That's my ellipses sitting right in that box. You with me? So there's what it would be if it was a plus in the equation. And that's what it is if it's a minus in the equation. Of course, you have two different ways to go out from the ellipse. You can either cut your ellipse like this, or you can cut your ellipse like that. Right? So in this case, if you wanted to go that way, that one would go this way. Does that make sense? It's almost too easy to trust, I think, sometimes. Right? Especially if you read through all the technicalities of what goes into these things. That seems pretty damn easy. And it should. So you guys try one. So remember the form of a hyperbola just like an ellipse, right? So if something's not the right way, you've got to force it to be the right way. Actually, mask it. I'll change it now.